Check, check, check. Aristides, you want to start now?
So hello, everyone. It's a great pleasure to have all of you joining us online, and a few of you joining us physically here in the classroom as well here in Edinburgh. I suppose there are going to be lots of people joining from all over the world, which is great. And we have the pleasure today to have a very nice group of colleagues presenting their work on PyPSA. Those of you who haven't heard about PyPSA before, PyPSA is an open platform for whole system modeling for energy systems that is being developed by people working collaboratively from many different places over the whole world, really. So to introduce our speakers today, we have Max Parzen, who is a PhD student here at the University of Edinburgh, working in our group. And he is a founder and the co-director of the PyPSA Meets Earth initiative. And he's a core team member and developer of the whole PyPSA ecosystem. We also have Professor Davide Fioriti from the University of Pisa, who is a co-director of the PyPSA Meets Earth initiative, and he leads lots of the software activities in the PyPSA initiative. And his overall research interests are within the area of macro and micro energy system optimization, economics, and computer science. We also have Leon Schumm. Leo is a PhD student at TU Berlin and Regensburg, and he's co-leading sector coupling activities with his research focusing on decarbonizing the energy system in integrated analysis and an integrated analysis of Morocco's hydrogen exports. Denise Giubilato is a master's student at the University of Pisa, currently visiting here the University of Edinburgh, and she is working on developing mini grids with the support of open energy system tools like PyPSA. Myself, I didn't introduce myself. I'm Aristides Kiprakis. I'm a professor here at the University of Edinburgh. I work with Max, and we are all members of the Agile Energy Systems research group. I'm going to be chairing this meeting today. So without further ado, I will leave the floor to our speakers. I will be, as soon as I leave the microphone, I will turn on my laptop and join the call so that I can look at the questions that people online may be asking. So if at any point you have any question, please type it in the chat area, and then later we will have the opportunity to discuss it. Similarly, for those of you in the classroom, you will have the opportunity to ask questions later. So, Max.
Yeah. Thanks, Aristides. Thanks for the introduction and introducing the whole event. Basically, we're having today a really nice question that is really going through that webinar, and that's how open energy modeling can save the planet, and maybe how that can also unlock potentials in research and industry. I actually posted before that I don't really believe that open or any modeling can save the planet itself. That's mostly about, the human actions that are behind that. But modeling is actually informing decisions. And a colleague just from the JRC, EU JRC, like he moved just on, Matteo, he just mentioned to fight climate change, we need to make the right decisions at the right time. And to make decisions, we need good information. And this is really where we think open modeling can really help making better decisions. And that's the key part of it. But let's see, and let's go through that slides. Well, it's not working. Okay. So yeah, I'm basically just preaching a little bit Tom Brown's slides, and I'm just doing that also by purpose, because actually the whole open source community, it's about sharing really nice content and just, you know, spreading the word on what we do and how we do it. And when someone did a great presentation, why should I just, you know, do some from scratch? And that's why I'm doing it, just by purpose a little bit. Let's see how it goes. I'm not Tom Brown. I can never replace him. But yeah, let's give it a try and see what is this open modeling stuff about. So we're starting with the motivations of openness and transparency, go through the PyPSA ecosystem, so what we are working mostly on, and then we share some experiences actually from the industry with the different model solutions. Openness and transparency. Why is energy modeling in particular? Can we remove the bar somehow? No. Okay. Why is energy modeling actually really interesting? And what makes it special is practically that energy has, in general, high social and economic impacts. And I think that's what we all see on our electricity bill at the moment, because, you know, people made certain decisions. We are really impacted by the current situation. But it's not just the electricity bill, it's also about health and, you know, all the conflicts, resource conflicts we're seeing around the world. There's a large role for business interests. I want to place my certain industry in countries where electricity is cheap, or where do I have enough heat and that kind of stuff. There are also large uncertainties about the future, that technologies might evolve. Batteries are super cheap now. I have many trade-offs in general. For example, the discussion about should I build an infrastructure for gas pipelines, or should I go for hydrogen pipelines, or should I just extend the electricity network? So that are some kind of trade-offs. And now with, I mean, renewables, we really need more land use as well. Should we use that land for, you know, our crops to get some food, or for our energy? I mean, that kind of discussions do we have as well here. And because everything is so complex, there's a need for computer modeling, and that's mainly used at the moment to avoid bad investment decisions, and in a way to save the planet. And all this modeling stuff is really depending on inputs as well. What is my data input? What are my constraints in the model? And that's actually a special part in that energy modeling. So what is open modeling? Open modeling means really that the whole chain from open data to the final report is fully transparent. And actually, open just doesn't mean only transparent. It also means that I can download, inspect it, edit and modify my data or my source code, and redistribute it with changes. So this is really the meaning of openness in this context. For sure, there are different kind of licenses, but when we speak about it, we mostly want that because that gives the full value. Yeah, then moving on, how does this openness and transparency really benefit the people? A couple of points. It increases just, you know, the transparency, reproducibility. I can now reproduce my research quite easily. I was just visiting a colleague and a professor in Dublin, and actually he mentioned that he tried to reproduce some kind of research in his early days when he was at 30 or so. It took him 1 year to just reproduce another person's error. And actually he found a way then to correct it, but it just took a year. which could now with open source take a couple of weeks to figure that out. We also reduce duplication efforts. We don't need to reinvent the wheel all the time. It's really highly customizable. It can really change everything and modify everything. It enables new actors to participate in debates. It's pretty cool when we speak about policy decisions, let's say the Green Deal. All that stuff could be then now debated and reproduced. It can improve the research quality in general by getting easier feedback and correction suggestions. It allows easier collaboration. And really the complexity that we see in that energy modeling part, there are now more sectors. There's much more detail we could use in general. And that's not something one person or institute can tackle alone. And that's really why yeah, we can just, you know, work together on solutions and get some time for other things. And it increases then, I mean, if things are open, it tends to increase the public acceptance as well. There are a couple of common objections to open modeling or that kind of stuff, because it is an extra step that you have to take to share things open in general, and or you're getting the skills to be aware of the whole process. And so people say it's too much work to prepare and support stuff. I think you don't have to do it in the perfect way. A really good way is, you know, just to, I mean, that's how you could start, share your code with a good license, just openly. Maybe you already help a couple of people having the same problem. Another objection is that they don't really see a benefit to themselves. If you're a researcher, there are a couple of benefits actually, and one of them is that all this open source and open data articles, they're really highly cited because they create a community around that. You can inspect and understand things quicker in a community, so it's really popular. Another objection is that people tend to defend their personal work a little bit. So they put a lot of effort in their work. But yeah, if you don't share it, another person can do the same. Like you're not the only genius in the world. They can do the same, but you waste, like another person wastes another 10,000 hours. So maybe that can be avoided. And yeah, then another objection is in general that people think there are mistakes in the code or in the data. And actually, it's quite nice because nowadays with this open source stuff, you can really point out the mistakes. You cannot just, you can complain, but you can also point that mistake out. And we can make it better together. And nowadays, there are actually in the energy modeling space a ton of models. They first appeared a little bit before 2010. Now we have more than 80. There's, I mean, for sure, a boom now. People discuss, okay, that we actually don't need more models. We actually need to now make sure that we work together somehow, because now people just share their code, but now we need to, the biggest challenge is to somehow work together and find ways to work together to avoid creating another 100 models. Yeah, and the push really for that movement here, for that 80 models, is that you know, governments requested that everything need to be open source. Yeah, and saying that, okay, now we have a lot of models and frameworks. A really valuable thing is actually data. All tools need data, and that's a lot of work. I think a common perception, so in the machine learning area, is that okay, 80% of the time we work on data, and or maybe 15% on testing and 5% or so on the whole machine learning code in general. And that's, I would say, quite similar for that modeling aspects. So we work a lot on the data part and not, creating this formulas and that kind of stuff. So that's super hard work, and that's where we should maybe focus in the next 5 to 10 years. Some examples, what we're using is spatially and temporarily resolved demand of electricity. That's really common. Electricity, like transport, heating, and industry demands, for example. So that would be super helpful, having distributed demands, having good profiles for buildings, for a whole region in general. Yeah, and just jumping a little bit, being aware of the time conflicts. There's a really nice group initiative in that space. If you haven't joined, so I can really motivate you to just signing up here. It's the Open Mod initiative, and there's content and events shared in that open modeling space. And just moving now to the next part, we just talk a little bit about PyPSA. We have around five more minutes. Okay, PyPSA. What is PyPSA? PyPSA is practically one of these open source tools focused on high resolution modeling. Like you see here in a European plot about how we create a model for Europe, can now be created also for other parts in the world. Leon is talking later a bit more about that. It's really filling a gap between power flow software, so Power Factory, for example, and energy simulation software like Plexos. And Tom Brown and his group and colleagues at this time, they really got really inspired by that Power Factory. Like Tom was annoyed by Power Factory, and he thought, okay, let's do that in open source way and create something really nice from that perspective. Yeah, and basically good grid modeling is also an important aspect. Like many tools disregard that, but especially for integration of renewables and the general electrification part, the grid plays a major role, and having that representation included is really important. So just scanning through a little bit through that capabilities. What can PyPSA do is capacity expansion planning, market modeling, nonlinear power flow, AC power flow, general components that are included, AC and DC power networks, generators with unit commitment, renewable generators, storage conversion, power to X technologies. And the back end of the tool is really typical Python pandas data frames. There's an own whole like optimization framework behind that, an alternative to PyYomo actually, that is a bit more performant, this new solution. And that new optimization framework has also solver integrations to all the COM solvers, and you can do then the greenfield, brownfields, and pathway planning. Super customizable. I mean, it's just open source code. Then just to give you a little bit of a picture, like where the tools are used around the world. Yeah, I think we see like Alaska, it's not so popular at the moment. Yeah, and yeah, the other parts of the world, I think the adoption is quite good. And now just a couple of examples. So how is industry using that and why they're using that? There's one example of the German transmission system operator, TenneT, Transnet BW, sorry. TenneT uses something else. And basically what they did a 2050 study on how to decarbonize Europe. And why did they use that? Why they didn't use commercial software for that purpose? They found it easier to build on, and they didn't have to reinvent the wheel because there was a European model. They could really just quickly use the tool. They were flexible with all that power to X solution. So they just used it for that purpose. Another case is the nonprofit TERI, so Energy and Resource Institute there, and they also used PyPSA for 2030 a power system study in this case, and their motivation was really it's easy to customize, lower cost. I mean, it's practically for free, so it's much lower than I think the 20,000 you have to subscribe for Plexos for one license. It's good for building up skills. You know, they have a lot of people and they want to develop their own skills. So they just use the open source in this context. And just recently, this year, Amber came out with a study about UK. And what was really cool here and really like respect on that move is that they shared also all the code and the data on how they created that scenarios. So we see now that actually people that influence policy making here in the UK, for example, you can really reproduce that from the beginning, from the data to the model to that report at the end. You can share everything fully open and benefit then from the engagement in the community. And then there are a couple of other examples. So the Rocky Mountain used that. I'm just running out of time, so I just wrap up. There's then also now the PyPSA Meets Earth initiative. And I think here I'm just handing over to Leon, who is talking a little bit more about the initiative itself. Yeah, Leon, please. At the end, we also have like 50 minutes of questions, roughly. So we need to switch now. Okay, great.
Okay, awesome. Thank you, Max, and thank you everyone for coming or listening online. So yes, I'm Leon. I'm really delighted to be here in Edinburgh and to speak to you and with you. And before we dive right in, I want you to have a close look at the picture. What do you see there? And I mean the background, not the cool picture in the front, but look at the back. And what you think you're seeing there might be a little bit different than it actually is. But that's something we'll speak about later. First of all, to start the presentation, we have like three major parts. First one is the PyPSA Earth initiative and the PyPSA model. And then we also look into the sector carbon model. And finally, also some output results. So looking into PyPSA Meets Earth. So Max has been talking about PyPSA and European models, but PyPSA Meets Earth is another initiative, also part of the ecosystem, which well, tries to accelerate the energy transition and to enable a clean energy systems worldwide. And for this, PyPSA Meets Earth is located in a set of different models or basically initiatives. So we have the PyPSA framework, which you can see on the very right, then some European models, and PyPSA Earth is the kind of newest baby in this area. But we're not only doing frameworks or models, we're also, as Max mentioned, lots of data stuff. And for this, we have separate little repositories. They might seem little, but actually there's lots of work behind it. For example, we have AdLight, which creates renewable energy profiles and also potentials. some cool satellite imagery, also some demand creator where you can use also artificial intelligence to predict demand in future, and many more tools. And these are just, well, part of the PyPSA ecosystem. And what we're doing with these models is basically creating a huge problem. And someone needs to solve these problems. So that's what we have other things for. That's, for example, LinoPy. That's an interface between the models and the actual solver. And for example, we can use the HyX solver, which is also open source. And if you combine all these, you can have like a really great model with nice outputs you will see later on. So why would you want to use PyPSA? Obviously, it's, I don't know, it's a fun name, it's cool, it's fun. But not only that, it's really skyrocketing. So if you look at the GitHub stars, so it's kind of indicating how popular a certain repository or model is. Then you see that PyPSA is really, well, much more popular than, for example, Osmosis or Onset or other similar models. So PyPSA might be the horse to bet on. So let's speak a little bit about the model called PyPSA Earth. The model is made up out of two things. Number one is the data. So for the data side, we have, for example, lots of GIS, geographic data, non-GIA data, and there's lots of work in data creation and fusion, modification. And this is basically part one. Part two we need is the framework. And the framework is called PyPSA. And also we have a solver there. And if you combine these two things, the framework and the data, you finally have a model. And if you solve this model, you will get some nice outputs. And PyPSA Earth was based on PyPSA Europe. This is the European model. But we're also developing lots of new stuff. So for example, we have now a great OpenStreetMap integration. We're using global land covers, but also doing lots of new functionalities. Mainly necessary because the data is a big issue in big parts of the world. For the European models, we have lots of great data, but for the Earth part, there's more work that needs to be done. So let's look at one of these outputs of PyPSA Earth. On the right-hand side, you can see Nigeria in 2060. On the left-hand side, you see Nigeria in 2020. Well, the country looks pretty much the same, I guess, but there's a really huge difference, and this is the energy system, or in this case, focus on the power system. So on the left-hand side in 2020, you can see lots of gas in the south of Nigeria, also some hydroelectricity, and these two are the main pillars for the energy system in Nigeria in 2020. But looking at 2060 on the right-hand side, the picture changes completely. You see lots of yellow circles, which are solar energy, and also battery inverters. So the energy system in Nigeria is based on solar and battery, but we also have more transmission lines. And yeah, combining these, we do even have a cheaper electricity price than today on a fully renewable-based energy system. So coming to the last part, which is PyPSA Earth SEC. This is the sector coupled model. What's the difference between a model we've previously speaking about and a sector coupled one? Now what we have is the whole energy system. So before we were talking about electricity generation and demand, but that's it. And that's where PyPSA Earth SEC comes into play, the sector coupled version. And you can see on the picture that we're now focusing not only on electric demand, but also on heating demand, transport demand, and looking into industry. And well, on the left-hand side of the picture, you still can see what sources we use. That's often renewable energy sources, but also any other sources. All right, so yeah, one of the challenges is to actually develop this model in a sector coupled way, but we still use PyPSA Earth as a base, and then we extend it. And luckily we have some, well, presentation or some results. Again, on the left-hand side, you can see Morocco. In blue, there's lots of transmission lines, which is gathered from OpenStreetMap and several regions of Morocco. And this is an input data for PyPSA Earth. And what we then do, we rely on PyPSA Earth. And within PyPSA Earth, it's also simplified the network, and we have certain clusters and nodes. And we use this model in the sector coupled version to extend, for example, hydrogen pipelines, and also add some hydrogen demand or some other sectors we need. And we can also have a look more into detail later, or if there are any more questions about the model. But for now, we'll move on. All right, so you've heard a little bit of PyPSA Earth. It seems to be a cool model, but there are also some arguments against it. So why would you not want to use it? For example, some people say, okay, PyPSA Earth is too complex. Or they say, okay, data interfaces are not clear. I want to change things. I want to modify. I want to integrate my own data. Or for example, there's an argument to say it just takes too much time and need quick results. And yes, indeed, there are some use cases where building up your own model makes just more sense. So PyPSA Earth is not for every use case, but for a lot of use cases, it's just a really good choice. Why is it? It's simple to execute. So if you're doing not much changes and don't have any specific national data you want to integrate, it's really simple to execute. It's just basically one line of code after you manage the installation. Then still you can do lots of configuration. So we have a configuration file, which is rather easy to understand. So there you can modify the potentials, you can set a CO2 limit, and many more things, which gives some kind of flexibility. And then one really cool thing about PyPSA Earth is that it's global. So many people all over the world are using already PyPSA Earth. And they just take the model, they look at it and be like, oh, that's cool. They try to apply it, maybe it works. And often they might see some bugs. They'll be like, oh God, this doesn't work. This doesn't make sense. And then what they do, they try to fix it. And that's the amazing things, or something that fascinates me. If you're, for example, building a model for Kazakhstan and you're seeing a little mistake there and you fix it, then you're not only helping your own model, but also, for example, someone who builds a model in South America. And that's really a nice idea. And well, as I mentioned, we have many users. It's pretty active and a great community, which, yeah, you're more than welcome to join. So how to be part of the team? Well, I think you managed the first step already. You're listening to this talk today. You can also come up to us later. You can ask questions. And basically, we're really involved. We are on Discord, on GitHub. We have open meetings you can just pop in. And yeah, if you have any interest, then just let us know, come to us. And yeah, it's definitely an exciting journey, which also brings people from all over the world together. So today in the first row, I see people from Italy, from Russia, from Germany. There's all just here for PyPSA Earth. So now you've probably been wondering, okay, wow, cool model, awesome slides. But you've just been wondering or looking at the background, what is it with the globe? What's so different, or where's the twist? And the thing is, when I looked at this picture, I thought, okay, wow, we're probably, oh, that was too quick. We're seeing Earth here. Okay, yeah, that's the planet Earth, that's right. And when I thought, looking at it, I was like, okay, there's probably, I don't know, it's not 20% of the Earth's surface, maybe 10%. But then I did the maths. And how much is it? It's only 1% of the Earth's surface we're currently seeing here. The solution was right here all along. So what I want you to see is the whole picture. And this applies for energy modeling and for pictures like this. Until you don't do the maths and you think you know what it is, you don't really know what's going on. So I want you to see the whole picture and not just the 1% as you're currently. Thank you. And yes, now I ask Davide to come on the stage.
Thank you very much. I'm Davide Fioriti from the University of Pisa, and today we are going to say that Max and Leon have told you about the large problem, the energy transition at a world scale, but we should not forget that we have to think big, but also small. Think big, but look at your neighbor. And not only that. In particular, I'm talking about the microgrids today, and maybe when we think about microgrids in Europe and in UK for sure, you think about something smart grid, smart energy systems, and everything smart. And so I took this picture that is from New York to represent this concept. But actually, the picture for microgrids is not always like this. In particular, if we go in Africa, the concept of welfare that is linked with the microgrids in developed countries changes completely, because the focus is more for surviving, basically, and growing. Because here electricity means having the electricity to run the fridge to keep vaccines, having the electricity to keep the fridge and maintain the food for the next days. And these are concepts that are given for granted. Electricity for the mobile phones to connect, to have information. It's to the radio that are absolutely given for granted here. So today I'm going to think about this, and in particular, highlighting that energy and electricity is something that is really connected to all the aspects of life. You can heard of water, energy, food nexus, and many other type of nexus that are here represented. Energy is a key elements for water, food, education, and health all together. And if you look at the maps on the side pictures, you can see that all the lacks of this access is concentrated. It's a correlation because it's not causality, but energy is highly big factor for growth in all these elements. And when combined, energy is a key aspect that has to be addressed. And in particular, I will look at the picture for electricity that is represented here. And it's sad to say, but Africa is dark. Africa has access to electricity that is very low, and this is access of 2020. And it's for the entire population, so both combining rural and urban areas, and the rates are very low. And if we look at this picture for only rural areas, the values are even worse. But this picture does not represent the full picture that we have to face, and we have to account for when we look at the world picture that Max and Leon have shown. Because currently we are 8 billion people. The 8 billion child has born recently. And if we look at the picture in Africa, between 2018 and 2030, the total population is expected to double, which means that the lack of access to electricity now needs to be coupled with a higher increase of electrification, not only to electrify people that do not have access now, but the people that will be born without access in the future. And you can see in the picture that from now to 2040, at current rates, the population is not, without electricity, is not expected to decrease, more or less is stable, because the population rate is very high. So, and when we think about these large problems, how to solve them? Africa has a widely diversified and distributed disuniform population that is shown here. And if we look at an example that is Africa, that is Nigeria, we can see that if we look at Nigeria, there are various regions that are highly dense as well as sparse. I personally visited Laisamis in Kenya, that is in the rural areas in the northeast. And it's one of the many examples of villages that is supplied by a microgrid. The population is far away from the central cities, and that's why the typical way of electrifying through national grid is not the cheapest ones, at least for starting. A different solutions, clearly the same solution cannot be used to electrify the peri-urban areas of Nigeria, of Nairobi. And that's why the different solutions need different conditions, need different solutions. So what open source can do? Open source cannot do everything and alone. And Max has well said that. And in particular, what can be done is efficient, transparent planning. And in particular, when we look at the microgrids level, the electrification strategy that open source can help is to identify what areas are better served by the national grid, what are by the off-grid solutions, in particular microgrids, and also standalone systems that are microgrids in a small scale at building level. In a nutshell, if the existing infrastructure is a straight line black there, and the users or households are in black in the blue dots here, we can find that the grid extension makes sense for users that are relatively close to the existing infrastructure, while microgrids make sense, or off-grid system makes sense for the other regions, sometimes even close to the existing infrastructure, because if the demand is too low, it's not worthy to connect in an economic sense the users. And in particular, in this case, we can distinguish microgrids when the households are grouped, and solar standalone systems that are the other people in which building level is the cheapest approach. However, what is the optimal design, and is the electricity the only vector that is needed? We start from electricity because it's the main driver for modern appliances, but there is more, and it's going to be. So that's why there is the plan for PyPSA distribution that has the goal of addressing part of these issues. And in particular, thanks to Denise that she's going to talk later about the first attempts here, we are creating a package that is able to load the data from open sources, open data, and integrate them to be able to create a sizing of the generation for microgrids or standalone systems. And as expected, procedure to move forward are to incorporate multi-year dynamics and the optimal layout of the network. Obviously, as mentioned, electricity is not alone, and the same approach, in fact, may have applications also in Europe, but obviously with different data and different contexts. So thank you very much, and I give the floor to Denise.
Thank you for the floor. Good morning, everyone. My name is Denise. I'm a master's student in electrical engineering at the University of Pisa. Currently, I'm in Edinburgh as a visiting research student, and I'm here in order to develop my master thesis, which topic are mini-grids. Mini-grids are an aggregation of electric load of generation, which can be renewable generation or fuel-based generation. And in mini-grids, there can be storage as well in order to have some backup. Mini-grids can be thought as isolated from the main grid, but they can also be interconnected to it. And in this last case, if they are interconnected to the main grid, they always have to be able to separate from it and to work isolated. And for what concerns my thesis, as it was said before, I'm developing a package about mini-grids, which is called PyPSA distribution. My thesis is part of the PyPSA Meets Earth initiative, but before me starting my thesis, this package was completely empty. So I started from scratch, and the main goal is to building a complete package in order to optimize mini-grids in some areas of the planet, areas in particular where there is lack of electrification because they are rural areas and remote areas. And in order to do this, I'm using Python. Currently, actually, when I started, I didn't have much experience in coding, and now this is very challenging, but I'm building the network. I started from a very simple network, which was made by just one bus to which were connected some few components. Now I'm improving technologies of the components, and I'm adding more complexity, and I'm adding all the components that can create a proper mini-grid. And at the end of my thesis, the expected results are that given some input data, the output will be an optimized grid. As input data, the data which are required are data about generation, for example, time series for renewable generation, but also other kinds of data are needed, data about the loads. And currently we are planning to estimate the load through knowing the position of the buildings inside the mini-grids. We want to size, and another important aspect is that as an input to the software, the geographical coordinates of the mini-grid can be done, because it has to be noticed that it's possible to place the mini-grid everywhere in the planet, just saying to the software where we want to have the mini-grid. So this is very challenging. This project is part of the PyPSA Meets Earth initiative. PyPSA Meets Earth is great community, and I really hope that like during this morning you could get it. So if you now have any question, I may give the floor to Max or to the professor.
So thanks everyone for these insightful presentations. There are a few questions on the chat. I think we should go through them one by one. So let me just check the first one. It's okay. It's okay. So the first one is from Anas, asking if having new points or buses considered in Nigeria, if this is happening, or with a grid, with the current grid infrastructure.
So I think with, just to understand the question, new points, you mean that we considered new areas of load and that kind of stuff. Actually, we haven't done that. So what we're doing at the moment is we're taking the grid infrastructure as it is today. I mean, as it is reported in OpenStreetMap, which is quite good, actually matching with the situation, what, like how it looks today. But adding new points, that didn't happen yet. But that can be an option. Like I'm sure, you know, with satellite images, you can see, okay, where's some light, and you can just make buses or connections to that area and explore them.
Okay. So the next question is from Emil, asking about the availability of geological potential maps for subsurface hydrogen storage, and similarly for reuse potential of existing gas pipelines to retrofit for hydrogen. Is it something that is available or can be added?
So I'm not sure if, like, are you aware of it? So like, I'm aware of it, but okay, I'll just answer it then. So basically, if you use PyPSA Europe SEC, that's the sector coupled version of the model, there you definitely have some geopotentials for caverns, I guess, right? And there's also the gas infrastructure included. Like, definitely have a look into that and rerun that for your purpose, and see if that might help you.
Okay. So the next question is from Daniel, asking about comparison between PyPSA Europe and PyPSA Earth. As an example, if someone wants to model an isolated system somewhere in South America, which of the two versions should be used, or is there any difference between the two?
Thank you. So for if you want to model an area that is not in Europe, then PyPSA Earth provides you already the framework and the model to do that. In particular, in South America, it has been already validated, so it works. If you are interested in other regions that are not being tested, most likely it will work already. And if there are some problems, you can notify and also help and contribute to the community. If you want to model Europe, so the PyPSA Europe version is the most up-to-date version. Something is interesting to see, you'll be also to use PyPSA Earth to model Europe and see what are the differences that may appear using open global data with respect to the very detailed data that we have for you. That could be an interesting activity.
A small addition, so because you mentioned PyPSA Europe's SEC especially as well, the Earth model is mature mostly in the power model context, but colleagues like Leon is working here on the sector coupled part, and that, I mean, definitely is something which you can already test and, you know, expand it to that region. Saying that, we also, like, we're currently in exercise, what Davide mentioned, testing that in all the other parts in the world, the model, including India, China, Indonesia, Colombia. So there's a couple of countries that actually nowadays work, thanks to Katja here as well. And yeah, and it's really cool. Like, now someone checked it, it works. We can do planning studies in these countries. And I think that shows a little bit how we can actually collaborate and bring value, and another person doesn't need to start from scratch.
Okay, thank you, Max. And one final question here on the chat, specifically for the mini grid design. How many grids have been designed, and with what parts of the world are you focusing? I suppose this is for Denise.
Yeah. Thank you for your question. For the second part of the question, which regards the part of the world we are focusing on, actually we are focusing on Africa, because it's the place where they may need more these kind of grids, but it can be applied. The idea is that the package can then be applied and can be run all over the world, just giving the data as input. And for the first part of the question concerning how many grids I designed, just one. There is one grid, and it's made with one bus and other components that are connected to the bus, and the kind of components depends on what components you want in your mini grids and the availability of renewable sources and so on. So it depends of the specific situation. Thank you.
Thank you, Denise. I don't see any other questions on the chat. Are there any questions in the classroom? Anyone? Yes. Okay, so the question is, how can someone contact the group and ask more questions later? So, yeah, I suppose there is a website that you've already seen in the announcement of this webinar, and there are email addresses there to contact relevant people. Maybe we can add something in the chat here, just to remind people email addresses. Yeah, I think Ekaterina is doing it right now. I can see her typing. Okay, so if there are no other, there is another question from Robbie. Keeping the code base together is relatively straightforward compared with keeping some kind of coherent database across all the projects. Any comments on this?
I didn't get a question.
So the question is, keeping the code base together is relatively straightforward compared with keeping some kind of coherent database across all the projects. Any comments on this?
I mean, like, one thought is that we generally prefer if there's some kind of global database. And like, we love to build interfaces to global databases because they have a coherent format we can extract our data. And that's why we always suggest people contributing to that global databases. If you have a lot of single databases, the structure might be a little bit different. So that is complex. And then I think maybe, if I understand the question right, how to get a formatting framework, describing the problem in a similar way. From the data perspective, like PyPSA enforces a certain kind of logic, and that keeps us formulating problems in the same ways across the different dimensions, like from mini grid to macro systems. And yeah, so it's kind of enforced. Databases, and generally we are aware that there's a big mess if you have, for every country another database, but luckily we have some global databases as well. Like, someone wants to comment on that as well? The thing's answered. Okay. Yeah, Katja shared just our website. Yeah, perfect. That's our website, and that's really the point where you can reach out in the best way. There are a couple of email addresses as well to the lead contacts of each development kit. And yeah, you can just reach out there, and maybe also join us on Discord so you can explore what's going on. So like channel where we exchange.
Okay. So I don't see any other questions online or in the classroom. The time is now 1:02 here in the UK. So thanks everyone for joining us. It has been very useful talk. Thanks to the for people who presented PyPSA today. Hope that you all keep in touch, and yeah, enjoy the rest of your day.